Welcome back to sections 21.1 through 21.2. In this video, we'll talk about the inertia tensor, the principal axis, how we can find that, and how we can find the moment of inertia about an arbitrary axis, and we'll demonstrate that with example 2. Alright, so example 2 looks like this, by the way. So an inertia tensor, which I'm going to call an inertia matrix, because they're the same thing. This contains all of our terms that we've saw before. So we have, it's a 3 by 3, so we get IXX, IYY, and IZZ. So these are, so this diagonal here are the moments of inertia. So this is a Y. Let's make that very clear. If I go down the sides and over, I'm going to get my products of inertia. So the 3 down here will be the same as 3 up here, just with inverted things. So down this way, I get negative IYX and negative IZX. And over here, I get negative IXY. So again, if you know anything about matrices, I just went over the diagonal. And go over the diagonal. Negative IXZ. And filling this out. Negative IYZ. So basically this is the Y row, and this is the X column, the Y column, the Z column, X row, X, Y column, sorry, X row, Y row, Z row. And then negative IZY. And these guys are our products of inertia. And this is the same as this, this is the same as this is the same as this. The negative signs come from the derivation of this. When you calculate momentum, if you go look at the book, you'll see why they're negative. If I can find a principal axis, then, so again, we did that with our example 1, where we put it in the center of gravity, and then we oriented our XYZ axes for that body such that we got symmetry. If I can do that, my products of inertia drop out to 0, and I get this really nice one where it's just IXX, IYY, and IZZ. And so this is what we were dealing with our planar rigid body. And we got a bunch of zeros. This makes our math a lot easier with all those zeros, so we just have a diagonal matrix. So being able to get this to a diagonal matrix like this will later enable us, so when we get to section 21.4, we'll get what's called Euler's equations of motion. So remember, that's sum of forces equals mass acceleration, those kind of things. So we want to be able to do this, we want to be able to find the principal axis of inertia, if possible. All right, so next, if we know all of these quantities, we can then do a calculation to calculate. We can do a calculation to figure out the moment of inertia about an arbitrary axis. So the example has the classic kind of nail rolling around or cone rolling around, whatever you want to model it as. So about an arbitrary axis. So it uses all the stuff in the inertia matrix. So if I know, and so basically what we have is we will have all the stuff in this matrix figured out, and that will be figured out based on the point A, or G, or whatever that we had, and the X, Y, Z coordinate system that we originally started with. So I believe the example uses point O here, so I'll just put in point O. And then we want to rotate it, and so then there's some new axis that we want to put this into. And so our goal then is to use this equation, and we can figure out the mass moment of inertia about that one thing. So like for instance, if you remember kind of back to kinematics, if we can find that omega is about an axis, if that's the axis that omega is about, so say omega is about this axis, well, I want to know what the mass moment of inertia is about that. So we could figure that out. So the equation that we're going to use looks like, I'm trying to find it, sorry. I about, so it's going to be O to A. Let's see if there's a different way we can write that. Let's just use a lowercase a, because we're just going out to some point A. Generally, that's how it's defined. It goes out to some point. And so this would be like, if we write in a vector, we would say the vector from O to A. If this was the generic coordinate system, then it would be the vector from A to A. And then what I need to do is I'll need to be able to find the unit vector from A to A. And so you're going to see in your book, they're going to say the AA axis a lot of times. So the mass moment of inertia about that is equal to Ixx, the unit vector of x. Sorry, I won't, no hats. It's the component of the unit vector. So the component of that vector. There's no, it's a scalar. It's just the part of it. Iyy, uy squared, izz plus uz squared. So it's not a short equation. But a lot of this stuff will zero out a lot of times, so what we're going to find out. I'm going to run out of room, so I'm going to rewrite down here. I'll be right back after I rewrite that. Alright, so there's the long form. Let's scratch this out. So this is the equation that we're looking for here. So I about some arbitrary axis measured in the same coordinate system, so it starts at the same base point. So it's in the same coordinate system. It'll be xx times the unit vector to that, iyy to the unit vector to that, izz unit vector of z. So the unit vector is for this thing. So the unit vectors are all for our line. The xx, yy, zz, xy, xz, and these are all for the original orientation and point. Just, okay? Otherwise, it would make no sense to recalculate them, because if you could do that, then you wouldn't need this equation. So these are for the original orientation, and then these are the unit vectors of this line. To get that line, it's a lot easier if you can use your direction cosines. So ux being cosine of alpha, where alpha is measured from the positive x-axis to our thing. And then uy being cosine of beta, where beta is measured from the positive y to the positive. So make sure you put these things tail to tail. So notice that both of these point out and are common points. So the beginnings of them start at the same point. And then uz will just be cosine of gamma. And then we have the property. Where is that? Right, there it is. So the property being that cosine squared alpha plus cosine squared beta plus cosine squared gamma equal to 1. So you may not have to use that, but it can be faster in some cases. Alright, so let's apply this to example 2. Alright, so we have this, this looks familiar. It's one of those cones that rolls around a fixed point. It's not a great drawing, but hopefully, if you want to see the actual drawing, you can go back. Looks like that. So we want to find I about this z prime axis. So about this axis that we know is going to be the axis of rotation for this thing. We did that in the previous sections. So we're going to use our equation about an arbitrary axis. So iz prime is our arbitrary axis. It's going to be ix ux squared. So I'm going to drop the extra x off of that. plus iy uy squared plus iz uz squared minus 2i xy. So just writing the equation that we had before. And obviously the order of these doesn't matter. You can change the order to be whatever you want. Alright, so squeeze that in there. Sorry, I ran out of space there. So there's a lot of stuff that we need to find. So keep in mind that all of these unit vectors will be about our pink axis there, and the other stuff will be about our original axis. So these will be like the inertial properties, all the i's, about the original axis z. So we have, basically, we have y coming out of the page, we have z that way, and then we'll have like an x axis this way. So if you think about the coordinate system, it's kind of like slanted like that, where there's, something like that. So what I need to do is find all of these parts. So let's start out by finding Ix. So Ix is the mass moment of inertia of this thing. So I'm going to kind of draw like a side view over here. So we have this slender rod, and then at the end of it we have the side profile of this disk, and then we have our point, and so this is X, and then this is Z over here. So side profile, and then we can just rotate that up to get to our just put our Z, so our Z prime axis is now pointed down this way, which may be an easier way to look at it. So we need to have, let's call this point down here point A, just because it's an arbitrary coordinate system. You can call it O if you want. I can call it the origin. So if I want to get Ix at that point, then I need to get the rod about A and the disk about A. So if you think about it, Ix and Iy are actually going to be the same. So if I redraw this, Iy is going to look exactly the same. If I redraw this diagram with a y kind of pointed off to the side, if I have like a top view of this thing, it's going to look exactly the same. So Ix and Iy will be exactly the same thing. So I don't need to actually redo any calculations for that. So once I find one, I'll find both. So for the rod, we can look up the equation for a rod about the endpoint. It's going to be 1/3 mass length squared. So 1/3, its mass is 1.5 kilograms, and its length is, so it's 300 millimeters, which is 0.3 meters squared. So 1/3 ml mass length squared. For the disk, so the disk is all the way out here. I need to move it back. So first I need to find about the center of a disk, and then move it back. So we're going to do some parallel axis theorem here. So its initial thing is going to be 1/4 mass and radius squared. So its radius is 0.1 squared. So again, you can look those up in the back of your book. Then we need to move it this way. And that is going to be mass distance squared, so 4. And then we're going to move this, so we neglect any thickness of this, so we're just going to move it the length of the rod, which is 0.3. So this is just parallel axis theorem for the disk. We run that calculation, we get 0.415 kilograms per meter square. I should probably keep an extra sig fig on that. Alright. Okay. So now, let's find IZ. So I have X, I have Y, I need to get Z. So Z, if I draw the end of this, up here, I basically have the rod, and then I have the disk, and let's have X pointed up. sorry, x points up. I know it's a little weird. And then if the rod's coming out of the page, then y will be to the left, following our right-hand rule, because x into y, my thumb points up, which is the same direction as z. The rod doesn't have a thickness I care about, and then this has a 0.1 meter radius. So that is again going to be I rod plus I disc. Both those conveniently are going to be about their center of gravities, because it's the center point, it's the midpoint for both of those. Again, I rod is just 0. It has a negligible thickness or radius. We don't care about it. So we just use the disc, and that ends up being 1/2 mass radius squared. So 1/2 times 4, 0.1 squared, which is 0.02. All right. So that's all of the mass moments of inertia. So now we can get the products of inertia. So if I come up here, this is our xy plane. Hopefully you can see, so we are at the center of gravity. If I look top and bottom over the y plane, we're symmetric. If I look left and right over the x plane, we're symmetric. So I can see that I, x, y is 0. Oops, you can't see that. All right, ix, y is 0 due to symmetry. How about, so xy and yz will be the same. So they're both going to have this this looking plane here. The xz plane and the yz plane will both look like that. So I'll move that down here. So ixz should be the same thing as iyz. Those planes will have the same drawing in them, roughly. So they're going to be let's see. So again, we have this kind of shape, which we can do as a rod and a disc at the end. We're going to add those together. I want them both to be about an endpoint, so let me mark the endpoint here. So they all need to get down here to the endpoint, and this endpoint will be kind of farther away, so I can't really get it on here. It's kind of over here. It's not on the body, it's off the body. For that case, I should have left some more space. So this one has a center of gravity right here. If I drew my xy axes, so they are parallel. They actually share the same z. And this can be x or y, depending on what you need it to be. So this would be kind of like a prime. You can think of it being like right here on this body. Sorry about the freezing of the video there. So you can see that this is 0. So its ixy prime about the center of gravity is 0. Good. And then if I wanted to move it to the left, well then I would say that it's 0 plus mass distance x or y. Let's just say distance x for right now, and then distance z, and that's the important one. So distance z is never going to go up or down. So distance z is going to say that it is 0. So therefore it's 0. So this is going to have a 0. And then by the same logic, this one's going to have a 0. So I'm going to get symmetry. So again, this will be my z-axis. This will be my x double prime, my y double prime axis. And then I'm going to move it a whole bunch this way, but I'm never going to go off the z-axis. So I'm going to get the same effect. So in essence, these are both 0. Again, due to some symmetry and just analyzing the problem and looking at it. If it wasn't 0, you could calculate it. But makes it nice. All right. And then the last thing we have to do is we have to get our unit vector. So we have this triangle. Oops. We have this triangle right here. So let's use that to get our unit vector. So remember, our so we have a 300 here. Oops, I drew that poorly. It is this triangle here. This is our 90. So this is 300. This is 100. This is our hypotenuse down here. So we're going to use, we're going to find theta here. How far down did we tilt this in the z direct? Over the, basically we're rotating over y. So theta is going to be tangent inverse of opposite over adjacent. So 100 over 300, and you get 18.43 degrees. That's what we moved down. And so you could use this to calculate a new vector, but we can just use our unit, our direction cosines now. So ux is going to be the cosine of alpha. So alpha is going to be this 90 degrees here plus the 18 degrees here. So I have 18 degrees right here plus whatever. So it's the 90 degrees plus the 18 degrees. So 90 degrees plus 18.43 degrees. So that's my unit, that's my ux. And it is 0.9487. My uy is just cosine of 90 degrees. So again, y is basically just straight out of the page here, and so I'm just going to go straight over there. So 90 degrees. Cosine 90 degrees is 0. And then uz is going to be cosine of that 18.43 degrees, which is going to give me, oops, sorry, that's the 0 point, messed up my numbers here. That's the 0.9487. This number up here is negative 0.3162. There we go. So let me grab a piece of paper and we'll continue this. Alright, so I've rewritten it on this new piece of paper, and we know all of the values in here, so let's just plug in what we know. So we know that Ix is a 0.4150. Our u of x is a negative 0.3162, and we're going to square that. Our iy is going to zero out because u of y is 0. Our iz is a 0.02, and then our u of z is 0.9487 squared. And then I get over here to these. So this one goes away because I have a u of y. Same thing's going to happen over here with this one. I'm going to get a 0. And then this one will zero out because my ixz is 0. So then I just get plus 0, plus 0, plus 0. So I just have those two calculations. You plug that in your calculator, and you should get 0.0595 rounded kilograms meters squared. So that would be your mass moment of inertia about that new axis. And again, that's a standard cone kind of problem. So you could then use that to do other analyses. So just recapping, we had basically a cone rotating about a fixed point, represented by a rod and a disc. We have our generic equation to find the moment of inertia about any axis. So this was originally defined in an x, y, z, where y is coming out of the page and then x is that way and z is that way. We found this angle is 18 degrees using some trig. Again, that trig down here. We then proceeded just to find Ix, Iy, Iz with just the stuff that you've done before. This is a rod about an endpoint. This is a disk about its center, and then we move it using parallel axis theorem. Iz is just a disk about its center. The rod doesn't have a size that we care about, so we neglect it. And then for products of inertia, we were able to cancel out a bunch of stuff due to symmetry. So xy was symmetric about that plane if I put the coordinate system at the center. And for xz and yz, we're able to show how it became 0 by looking at the combination of the rod and the disk and then moving them along the z-axis. Since we never went up or down on the z-axis, the mass distance squared kind of term. So it's not mass distance squared, it's mass delta x delta z, or mass delta y delta z. The delta z was always 0 because we never went up or down. So we always got a 0. And then finally, we found our unit vector using our alpha, beta, gamma angles. And there's other ways to do that as well, but that's generally going to be faster if you have an angle already. All right. So hopefully that helps. If you have any questions, feel free to reach out.